So here. Also, I wish to start with some information for you that I have found quite a good lecture notes from other university, yes, which basically goes through the topics we discuss more or less, yes, about capacity of the channel, about fading, Doppler shift, and basically also equalizers, which we are talking today about. So I would recommend you to actually study this material too. I have provided you this PDF file in the Ortus system as an advanced material here. Yes, for today's lecture. So these are quite good lecture notes to recommend you in this course. Yes, because basically it covers intersimple interference, it covers filters, which we have already discussed. It covers quadrature amplitude modulation, complex constellation, and basically more or less all topics we are talking about to some extent are covered in this material as well. So this goes for error probability analysis. Okay. And so forth and so on. I believe we had also noise, matched filters. Yes, these matched filters we were talking about for limiting bandwidth of the signal and at the same time avoiding additional intersimple interference. And well, basically you had in one of the practical exercises chance to observe that these filters actually also reduce the amount of noise energy affecting our signal. So then we will have Viterbi algorithm next week. Linear equalizers we are talking about today. So basically, yes, this is quite good for our course. Okay, so let us start with today's topic. And today, as I said earlier, we are going to discuss equalizers. So let me remind you in some brief reminder what we know so far. So far, we know that there is a so-called intersymbol interference effect, which is caused by effect of limiting bandwidth and basically which leads to replacing our rectangular shaped pulse with some basically oscillations. Yes, fading oscillations. Each rectangular pulse is reshaped with this form of pulse. And accordingly, the problem starts when we send our data, for example, in this sampling moment, 0, in this sampling moment, 1, and so forth. So you can see here that at the first time interval, our 0 impulse will have effect on it. And that is actually that intersimple interference. So it can be caused by incorrect filter, which we use to limit the bandwidth for our telecommunications, and by the channel itself. So we talked about that we can have transmitters filter. Yes, and we basically talked that we are using root of the raised cosine filter, RRC, yes. And then we have basically channel. Well, I'm skipping modulator part. We are now talking about parts affecting the bandwidth of our signal. So this channel is basically independent and we cannot really control much about it. So this is something we have to take into account, but cannot really design to meet our specific requirements. So if this filter is completely under our control, so the channel is not, and we cannot hope that it will be good for us. So basically, this channel is something we have to basically consider. Yes. Then we will have equalizer, which will be talking today. So this equalizer will be exactly that part that considers the channel. So basically, together, these two parts effectively cancel out each other. And then we have this receiver filter, which is also root raised cosine filter, the same as in the transmitter part. So, and all these four components together should provide our ideal amplitude frequency response. And, well, basically what we want to have is ideal amplitude frequency response and linear phase frequency response. So, because the channel is completely independent and basically arbitrary, we cannot really hope to achieve it basically at no cost. Yes, so we have to design this equalizer so that these conditions are met. So basically, we achieve this effect basically thanks to this equalizer, because these two filters already provide us with this opportunity. Yes, we already discussed that we have almost ideal amplitude frequency response. Basically, what is different from ideal amplitude frequency response is that it's not, how to say, not so brick formed. Yes, it has these slight transitions from 1 to 0. And in ideal case, we would want to have completely rectangular shape. Yes, which is basically not so bad. And for the phase frequency response, we have this linear phase. Yes, so this is met automatically for these two filters. However, for channel and equalizer, we have to find correct equalizer to actually provide us with the same effect. So yes, and now you can imagine that all we have been talking about so far in all our practical exercises have to be considered into real telecommunications hardware and software, yes, so that basically the system for transmitting data actually contains both filters, equalizers, yes, and evaluation of bit error rate, and so forth and so forth. So this all comes in together and happens at the same time in the Rayleigh fading channel, for example. So, as we can see from here, equalizer is our means of basically fighting the inter-symbol interference caused by channel. Yes, caused by Rayleigh or Rayleigh fading channels. So, and this inter-symbol interference, as I said, happens because a rectangular shaped pulse is replaced with some other form containing these tails, yes, which accordingly interfere with next symbols. So each of these symbols will produce this tail, accordingly interfering with other symbols. Yes, as you can see clearly here. And this leads to problems with reception of data. As I said, these channels are usually radio channels, yes, because we have multiple paths, and basically they are out of our control. Well, to some extent out of our control. We can use different frequencies, that is true, which have different propagation effects and different Doppler effects, but still, to some extent, we will suffer from this problem. So we can safely assume that basically it's almost out of our control. So here you can see example for quadrature amplitude modulation 16, which we have made multiple times in our practical exercises, and today we will again use these modulation types simply to the fact because it's very good and effective in modern telecommunications, and it's widely used not only in CAM16 but also CAM64, for example, CAM32. The general principle remains. All that differs is this number of total signals. So this is quite modern technique, which is one of the reasons why we rely so heavily on it in our practical exercises. So consider we have original constellation represented by 16 these points colored with red, and we transmit some specific symbol. For example, this one of the 16 symbol. So we can say that we sent 10,000 of the same symbol. So basically symbol, I don't know, symbol 5, symbol 5, symbol 5, and so forth. And we send the very same symbol 10,000 times. And what we receive is represented by these green triangles. So each time we send this symbol, all the time we happen to receive some point which is which can be basically located here, or it can be located here, or it can even be located here, yes, but they all are the same original symbol. And this inter-symbol interference affects it quite in wide range, unlike the white noise. If we were talking about white noise, we should get some small cloud around this point, and all the points, well, at least most of the points. It is still theoretically possible that because of the white noise, these symbols will eventually happen to be received at this symbol. However, the probability of such effect is quite low, yes, much lower than in this case. You can see that we have received many symbols with a quite large distance. And for the white noise, well, basically, the further we go, the less probable is this event, according to the normal distribution of probabilities. Now, this is Rayleigh distribution, and basically it makes possible quite to change for this value in quite a large boundaries, in quite a large intervals, yes. So this will happen for each of these possible 16 symbols, and you have already in practical exercise observed how it will look. Yes, even we have tried Rayleigh model with different k parameter values, and you have seen for yourself that actually if k parameter is quite large, then situation becomes somewhat better. It's still not good, but it is at least better than for Rayleigh channel. Rayleigh channel is something like the worst possible case, yes? So these distortions are observed. And if we try to detect this signal, we will receive quite large error probability, which in fact isn't even caused by noise. So regardless of adding noise, we still have this problem, yes? Even if we don't have any noise at all, we will have large number of errors, which was our previous practical exercise, number 4, I believe. Yes, today we have number 5. And accordingly, you have seen for yourself that, for example, for normal channels without Rayleigh or Rayleigh effects, we had bit error rate degrading exponentially. For Rayleigh channel, we had somewhat more like linear function, and for the Rayleigh channel, we had like plateau, which didn't even improve at all, with even quite large signal-to-noise ratio. So that was Rayleigh. This was Rayleigh, and we can say that this one was well, basically linear. Yes. And accordingly, what we want to do is to convert this Rayleigh into the linear. And the only way we can do so is by calculating some specific equalizer that will complement this channel. And accordingly, together, they will be a linear system. That is something what we want to do. And today we are going to accordingly discuss that. And you will see for yourself in practical exercise that even if we have this problem, when we calculate this equalizer correctly, we can actually hope to revert and compress all these points back to this single position. You will see, however, that it doesn't work ideally. There are some problems and caveouts, but still most of the symbols will converge back to this point after passing through this equalizer. So you can say that basically this picture you observe here is basically at the input of this equalizer, and at the output of this equalizer we will have these points back converged here somewhere in this more or less small cloud, similar to how it's happening for white noise. So basically we will convert this Rayleigh effect, this cloud, and compress it to be centered around this original center point of the basically perfect CAM16 constellation symbol. So that's what this equalizer will do. And basically, as you imagine, this equalizer has to consider the impulse response of the channel. So if the channel impulse response will change, then we will need a new equalizer. And well, we have already observed that for real Rayleigh channel used in practice, this impulse response is not stable. It's changing in time. And well, considering that, that will mean that equalizers will have to change as well. They have to be adaptive. We will conclude this lecture with some possible solutions capable of being adaptive, but of course this is quite complicated topic, good enough for entire course, so we will not really delve into adaptive equalizers, but still we will learn how to calculate fixed equalizers, and the idea can be then extended if you will need to encounter this in your career further. Yes, so you will be somewhat more ready for this well, basically problem and how to solve it. So as I said, the solution is to calculate equalizer to revert the effect of channel impulse response. And the thing what we are going to compensate is not really impulse response, but rather than that, amplitude frequency response. So here you can see how the frequency, well, basically amplitude of the channel output signal is affected by the frequency. Yes, so you can clearly see here that it's nowhere near being linear. So for perfect ideal amplitude frequency response filter, we should have 0 level at all frequencies, or at least some linear function. And here you can clearly see some changes. Yes, and accordingly, what we are going to do is to find a reverse amplitude frequency response, so that after multiplication of these two, so one is for the left part we have channel amplitude frequency response, for the right part we have equalizer amplitude frequency response. So what we need to do is to find equalizer with the such amplitude frequency response, so that it will be reverse of the channels impulse amplitude frequency response. So for that we need to know what channel is basically in our disposal. Yes, and there are some techniques called channel probing. Yes, channel probing. So this probing is needed to actually estimate the impulse response of the channel. The impulse response of any system actually is not so hard to get. You have to, so for example, this is some system with some impulse response we don't know. So you have to send a single pulse followed by zeros. Yes, if we are talking, for example, about discrete process. And then as a result, you will get some response, which is actually the response to this impulse, So it's quite simple. However, for real channels, this will not really work well enough, because this small single pulse has so little energy, so that our total impulse response, which has to actually have the same energy as this single pulse, will be quite low and quite difficult to work with. So for that reason, we send here special code word. Yes, code word, such as, for example, maximum length sequence, M sequence. Yes, you might have heard in your bachelor level course or some other courses in master's degree, yes, about this pseudo-random sequence generated. Accordingly, these can have much greater energy and still can be used to estimate the impulse response of the channel. Once we have this impulse response, we can calculate this equalizer, and accordingly, as you imagine, even if we need to adapt all the time this equalizer, this procedure can be repeated over and over again. Once again, we evaluate this impulse response once per specific time interval. So here you might remember that we can have fast fading and slow fading. So we need to actually know how fast is this fading, so that we can actually evaluate the impulse response at this appropriate time intervals, yes, and update our equalizer. But the idea for our practical exercise will be that this impulse response is fixed for the channel, and we have to find the best equalizer possible under some limitations, yes, some parameters we have specified. And basically, yes, that is exactly what we are going to do in our practical exercise. So here I'd like to mention that this is actually very similar to these audio equalizers, yes. So, for example, I don't know, I might even open some of my program for my headphones, yes, and we might open, for example, here Equalizer Preset, which you can control manually, yes. So this is our amplitude frequency response changes. So here we have frequency, here we have amplitude, and you can actually, set different, for example, for movie theater, it has this shape, which accordingly is expected to compensate some specific effects happening because of hall and large, basically, room, which makes our sound different, yes, and this is needed to compensate that effect. And similarly, we can have it even edited manually. Similarly, this works for telecommunications channels, but in different frequency range, as you might imagine, because there we have only audio frequencies, which you can hear, but for telecommunications, our bandwidth is also quite larger. For example, we might use 80 megahertz bandwidth or 5 megahertz. In comparison, for audio frequencies, all we have is 20 kilohertz, which is divided into multiple smaller bands, yes, and each of the bands you control. Here, however, we need to actually consider the channel. So equalizer in this sense is exactly the same thing as for the music playback equalizer, for video playback equalizer. However, it's just used for slightly different purpose, yes, to change the quality of the received radio signal rather than played back audio signal. And basically, that's how it works. Exactly as I said, we find equalizer's amplitude frequency response once we know channel's amplitude frequency response. So we might have a small demonstration next week on how this can be, But all that you need to know is that actually, if you know the impulse response, then by using Z transform or Fourier transform, yes, you can actually find the amplitude frequency response. So impulse response and amplitude frequency response are related to each other via Fourier transform, for example, yes, or Z transform. So if you know impulse response, you can actually calculate amplitude frequency response of the channel. And we already did so in our practical exercises, and today we are going to do so again. And similarly, if you know for the channel amplitude frequency response, you can calculate one for equalizer as well, just so that together they will produce some constant level, which is considered to be amplitude frequency response of ideal channel, or at least something very close to that ideal level, yes, which will be at any rate much better than what was originally here, for example. Yes, if we compare this black line, yes, with this original channel amplitude frequency response. So the only question is how this will help us. Yes, what we are going to do. Okay, we can find some filter parameter, design some filter with this amplitude frequency response, and then we can use it. And that's exactly what it is. It is going to be some sort of filter with specific transfer function, which is exactly this transfer function. Yes. So we at first we set our desired transfer function, in this particular case amplitude frequency response, and also we need to remember that at the same time we want a linear phase frequency response, yes, so that we can have how to say it, calculable amount of delay, so that we know when we have to read our data. Otherwise, if the phase frequency response is not linear function, we cannot really know when it is correct time to read our data, and this will lead to problems. Even though amplitude has been compensated perfectly, this will still will not be good enough. Yes. So say we need to calculate some linear phase filter, which at once basically dictates that we have to use finite impulse response filters, because they are the only kind of filters capable of providing our linear phase frequency response. Well, we can make something with close to linear frequency response for infinite impulse response filter as well, but this will be much harder. Yes, and basically these filters transfer function is represented by the coefficients of this filter. So if we look at the schematic of this finite impulse response filter, you will see that it has some delay units. Each of them is introducing z at power of -1. We have some coefficients, which are accordingly values of the equalizer impulse response, and we have this addition sum operator. Basically, that is typical finite impulse response filter diagram. Yes, I don't know if you had already the course on these filters in some way. I assume that you should have eventually mentioned them at least somewhere, but if you haven't, it's nothing like very difficult. You can just Wikipedia this term, yes, and find for yourself a lot of this information. And in fact, we already use these filters for raised cosine filter and root raised cosine filter as well. Yes, so these were finite impulse response filters because we have specified the length of the impulse response, which was a specific number. It wasn't infinity. Yes, it was, for example, I don't really remember, but I think we had like 5 symbols multiplied, for example, by 4 samples per symbol plus 1. So, for example, 21 so-called tabs, yes, where each tab is one of these coefficients, 1 tab, 2 tabs, and so forth. So here we have L tabs overall, which is basically by 1 larger than the number of these delay units. Yes, so you can see here we have tab, and here we have tab, and in between we have n delay units. So our signal after entering this filter at the input will be at the output exactly after n divided by 2 time intervals if and only if the filter has linear phase frequency response. So if it has linear phase frequency response, then we know for certain when we should read our data. Otherwise, it's impossible to tell when to read this data because it will depend on particular implementation of the data. So here I wanted to show you the overall idea of equalizing. So considering, yes, as I have previously mentioned, we can have fixed equalizers and adaptive. So now we are going to talk about fixed equalizers and their types. For them, a channel is considered to be basically non-variable process or system, yes, time invariant system also. And basically, once it has some impulse response, this impulse response is not changing at any time moment. In that case, we can calculate the equalizer one time, and this equalizer will be good for all the duration of communications. This can be basically also the case. I cannot say that this is some unrealistic scenario. Imagine, for example, some kind of radio relay stations transmitting signals, and here we have, for example, some lake. Yes, water is a quite good reflector of the signal, so you can have reflected signal arriving at this point as well. However, these base stations are some towers, yes, with antennas, and they are not going to move. Of course, they have some, movement because of the wind, because of the weight, and so forth, but this is minimal. But other than that, we can assume that this channel is somewhat fixed, yes, and for that we can calculate this equalizer for this particular place of these two particular base stations for this particular channel to be calculated one time and then put into the equipment in these devices, in these transmitter and these receiver devices, and basically it will work. Yes. Now for adaptive case, we need to consider that we are, for example, moving in car, yes, in some city, and accordingly the reflect, and here we have some base station, and accordingly basically we have these reflected sides, and as we go the situation changes and the impulse response will change as well. So for this case we have to use adaptive equalizers. The principles are more or less same. What is different is that we need to constantly update this equalizer. So for fixed equalizer, we do so once, we calculate this equalizer, and that's it. It's good enough. And for adaptive, we have to make sure that this equalizer is still up to date and still basically optimal for our purpose. Yes, that means that we have to evaluate the impulse response all the time. In this case, we can use some specific measurement equipment, measure this impulse response just once, yes, and then consider that it will not change because these stations are not moving. Here we have to provide some mechanism for this mobile device to be able to evaluate this impulse response by itself, yes, and we'll talk about it as well, how we can do so. Actually, sometimes we can even consider that we work in so-called blind mode. We don't know the impulse response, but we can try and adapt to get better results. But at least for now, let us consider that we talk about fixed some kind of fixed equalizers, that we have some channel with some impulse response HN, which can be calculated into transfer function by using Z transform for this impulse response. Yes, so this is the channel's transfer function, and in order to compensate for it, we have to find the reverse transfer function to these channels, so that equalizer's transfer function multiplied with channels transfer function should be some kind of constant. Well, ideally, of course, we would want to have 1 here, but in reality, of course, we will have some delay at z power of k, for example, yes, or z power of n divided by 2, as we already know. So we can have some delay here, but ideally we want to have 1. So let us assume now that for some way we can make this ideal case, and all that we have to do is to actually implement the filter with this transfer function. Well, Z transform usually represents some polynomial of the variable z with some coefficients, for example, like this, z minus 1, and so forth. Yes, which is a recursive filter because it has a feedback and denominator polynomial. So that means this is going to be infinite impulse response filter. Well, actually, I can show you a small, simple example of such filter, and you will understand why its impulse response is infinite. So here in the left part, I will show you finite impulse response filter. So for example, we have this delay line. Here we have coefficient 1. Here we have coefficient 1/2. And here we have this addition. So that is finite impulse response filter. And if we send the single impulse followed by zeros, then as a result at the first time interval here we are going to get 1, which is 1 multiplied by 1, plus here we had previously 0, plus 0 multiplied by half, and accordingly that is first sample of the impulse response. Next, this 1 will be stored in this delay unit, which is nothing more than memory cell, for example, random access memory cell, where we can write data and read data. And accordingly, next sample, we are going to read this value stored here, which will be 1. And at the input at the same time, we will have 0. So the next sample is going to be 1/2. Yes, 0 multiplied by 1 plus 1 multiplied by 1/2. Then all the next values will be zeros. That is for finite impulse response filter. Now I'm going to make an infinite impulse response filter. So basically like this. No. So I want to have here multiplier 1/2. Here a delay line unit. And like this. Wait, no, I actually don't want to have 1/2 here. I want to have it here. Well, it will change impulse response somewhat, yes, but I just want to have the beginning of this impulse response the same as it was here. And actually, I believe I should have minus 1/2 here. So what will be different? Different will be the following. For example, we send this 1. This goes directly to the output. This previous value was 0. And here we don't have this 1/2. And at the output, we have this produced as 1. Yes, also. So 1 at the input produces 1 at the output. At the same time, this is stored in this memory. Yes, and Okay. This is stored in this memory cell. And at the next time interval, when we send the first 0, this 0 will go straight to the X, and at the same time here, this 1 divided by 2 will be added and produce minus 1/2 value of the impulse response. 1/2. And it will be stored here. Next sample, it's going to once again be multiplied by minus 1/2 and go to the output. That will be 1/4. Yes, and so forth. So basically, it's quite easy to see that it will never end. It will be minus 1 divided by 8, then it will be 1 divided by 16, 1 divided by minus 32, and so forth. It will be infinite, although here we have zeros. Yes, so this will be infinite impulse response filter because it has this feedback, this recursion. Here we don't have this feedback. Yes, we don't send this input signal no way to the output signal, no way to the input. So this is the difference between infinite impulse response filters and finite impulse response filters. For finite impulse response filters, this transfer function will always be some polynomial like this. And in fact, the coefficients of this polynomial are going to be impulse response values. So they are also quite easy to implement. If you know the impulse response, then you know your filter, because these are these coefficients. Yes, and it has 1 in the denominator. Yes, so basically it's only numerator. For infinite impulse response filters, you can actually have both numerator and denominator, right? Like this. And in this particular case, we are going to have infinite impulse response filter. Yes. But as I said, such filters have in general non-linear phase frequency response. It is very difficult, almost impossible to calculate linear phase frequency response. Actually, it's still not going to be perfectly linear, but well, to some rate, it is possible maybe to generate, assuming that we don't have to change amplitude, but overall you cannot generate a linear phase frequency response and some arbitrary amplitude frequency response at the same time. You can only generate linear frequency response if your amplitude frequency response is going to be flat, like this. Yes, so this is going to be our IFR. And then it is possible to make a phase shifter with phase frequency response, which look like linear function. However, you already know that we cannot really hope that the channel will be linear. Yes, we need this equalizer IFR to be reverse of the channel's equalizer, and it entirely depends on the channel. And well, the bad thing is that channel's amplitude frequency response is not going to be constant level, right? So for that reason, these filters will not really work. And in fact, I have prepared some small demonstration for you to actually show you how it will work. So consider that we have some usual quadrature amplitude modulation 16 constellation sending some data, yes, in the channel, calculating in the channel we specified impulse response, so we can calculate this equalizer as an infinite impulse response filter according to this reverse function, yes, and basically we can see that it looks like it did help us. Yes, you can see now that after equalization, all these blue points have actually converged back to the symbols of quadrature amplitude modulation symbols. However, the problem is, although they have converged, they do not match, yes, so originals. So for example, here we can see some data. So the first column is original. So this is original. That's what has been sent. Here you can see channel, what happened to this signal in channel, and here you can see what we have received. And you can clearly see that, for example, for the first symbol, we have match. So we send this symbol and we receive this symbol. For the second symbol, it's not match. Although this is one of the points, yes, 1 minus 1i, that is particularly 1 minus 1i, this point, right, which is valid point. However, it doesn't match original data that has been sent. Originally, we had sent minus 3 plus 1. That would be so minus 3 plus 1. That would be this data. So originally we sent this symbol, and what we have received was this symbol. Yes, and basically that's an error. Yes, so we will have a lot of errors. And here you can in no way find when this will start to repeat. This happens because of delay. Yes, however, this delay is impossible to evaluate correctly. Yes, so for example, we can see that the beginning symbol is this, and we can consider that, for example, here, this next symbol should be like this. It's not, right? So this doesn't do. Next place where we have the same here. Yes. Again, this is not the real symbol. Next one here. Again, this is not true. So what I want to see is that I will see this entire column once I have counted this. And the bad thing is that no matter how many symbols I will consider, I will still never encounter this column. So it's impossible to use this infinite impulse response and get our real data. Now, however, if we use this finite impulse response filter and calculate it correctly, then we are going to get somewhat worse results, because we need to take into consideration that perfect converging of these blue points into the red dots will be happening only if the length of the impulse response is infinite, right? Here we truncate this length. For example, let us say we have this impulse response calculated. Yes, like this. And then we say that, for example, we are going to cut it off. For example, here, yes, to truncate it. And now we have finite impulse response. And accordingly, we have lost this, which made it more accurate. Yes, and accordingly, this picture looks worse. However, the fact is that now it will actually match. And if we perform later on the detecting of these signals, then you will clearly see that we have this data here. Yes. So the same way as it goes here. And these 16 values are this delay. So in this particular case, please note that we have filter order 31. So that means we have an delays of 31. And as I have previously mentioned, the reading delay should be the half, because the impulse response has to be symmetric with the maximum value at the center here. Yes, at the number 16. And then in both directions, it will go symmetrically. If the impulse response is symmetric, that is the only condition that has to be met in order to get linear phase frequency response. If the impulse response is symmetric, then the phase frequency response is going to be linear, and you can assume that you know that you should read your data at the end divided by 2. Well, of course, round it up like this. Yes, so 31 divided by 2 and rounding up produces us 16. And that is the position of the first symbol, which is indeed this first symbol, followed then by the second symbol, by the third symbol, and we have almost no errors. Well, some errors are still possible, but I don't think we will encounter here them. You will see, however, that in practical exercise. So finite impulse response filter in this particular case, although produced not so smooth convergence, yes, still mapped symbols correctly. So what has been received actually matches what has been sent, which is much more important. So let us now talk about how we can calculate this equalizer then, because this approach, what was, how to say, the most obvious and direct straightforward, doesn't really work. Yes, we have observed that for ourselves, that, well, unfortunately, it doesn't work correctly. We cannot really receive our data without errors. So we have to find another solution. And the most simple way is to use so-called zero forcing equalizer method. So consider that you have some channel impulse response available, and for example, it's represented by these 1, 2, 3, 4 taps. Yes. Then we need to calculate some equalizer impulse response. So the total impulse response is going to look like this. Here we have 0, oh, not really 0, but 1, yes, for our reading time interval. In this particular case, then our delay is going to be 8 symbols, right? And all the other symbols should get as close to 0 as possible. Now you can see here that actually, I will try to increase it, actually doesn't go directly at 0. So it is some small residual intersymbol interference, and we weren't able quite to calculate this precisely, yes? But still, the idea is quite simple. So what you are going to do is to actually find these numbers, yes, so that their convolution with channel impulse response, which is your task given to you, yes, basically doesn't depend on you, should produce as close to 0 here as possible. So basically what we can do is to actually calculate the absolute basically deviance from 0 in each positions, then add up together as a, for example, mean square error. Yes, and then we can try minimize this mean square error by finding more precisely these coefficients. This is optimization procedure. Yes, this is no way some mathematical method that we can rely on, that we can, for example, take some equations, calculate something, and then accordingly do something. So basically, this is more or less similar to some kind of machine learning problem that we have to actually use some optimization procedures to find the best impulse response values for equalizers so that they match these criteria. So this is our criteria, how we decide are these coefficients better or not. But basically we have to go through different values here to find them. Yes. Well, that is one of the ways which is the simplest to actually minimize it. You can imagine, however, that for adaptive it wouldn't really work quite well because optimization has to take some time. We might even fail in this optimization and find no solution. So considering that this impulse response will change in real world communications, then this method doesn't really do us so much good in all cases. Yes, it is good if we are talking about fixed. Yes, if we are talking about fixed, then we can spend some time optimizing some problem, find the best possible solution, and then use this optimum equalizer. That can be used for telephone line, for example. As you imagine, even the cable systems have their specific amplitude frequency response that needs to be corrected as well. So considering that telephone cable is more or less the same in all places, we can calculate once this equalizer for digital phones, yes, and basically mass produce it then and putting them into each phone. I'm talking about wired phone connecting to the telephone line, right? However, for mobile objects, this method doesn't really work because of the, first of all, potentially unstable solution, and second of all the time required to find this solution. So, as I said, we have to specify this optimization problem and accordingly define the target function. The target function is set to 1 at the reading time moment and as close to 0 for any other remaining time intervals. So that can be used to find this equalizer, design this equalizer. This method can work and we can actually even try this. However, we would prefer rather to use some more mathematical methods that somewhat guarantee our result, yes? So we can even basically write down multiple equations, considering that these h are, for example, h0, h1, h2, and so forth, are unknown variables. We can write down the same number of equations as we have these unknown variables, and then even basically, well, replace this optimization problem with some mathematically defined set of linear equations. Yes, so if we write down quite enough of these equations, then we can actually solve them. However, you need to consider that the solution might not exist, first of all, so we will have to find as close to this possible solution as possible. So even if we made this set of equations, it doesn't really mean that you can easily solve it. Yes, you might still have to resort to the optimization procedures. So for that, among other, for that reason, we are going to use some more advanced method, and this method will be used in practical exercise as well. So actually, even more technical details can be seen in additional material for practical exercise, MSE equalizer methods that can be used to calculate. And actually here we also talk about sample estimates. No. This is only for MSE. I thought we have here also, how to say it? Oh, sorry. I thought here we had also zero forcing equalizer, but we do not. Yes, so here we have only MSE equalizer. Here is some more theory, some code, which we will use today in our practical exercise as well. But overall, well, let's see how it works. Yes. One of the other reasons why we don't really want to use zero forcing equalizer is the fact that you need to remember that in addition to signal, we always have noise. Yes, and the bad thing about zero forcing equalizer is that it doesn't guarantee us that outside of our interesting bandwidth, for example, here we have this bandwidth, here we have this, I don't know, channel frequency response like this, for example. So we calculate some equalizer to compensate for that by finding this. And outside of this, we would like to have as close to zero as possible. However, the zero forcing equalizer doesn't really necessarily provide us with that. And you already know that if we do not suppress this noise outside of the bandwidth, it might actually affect decision making of the demodulator and accordingly lead to received error. So what we want to actually is to go as close and fast to zero as possible once we have provided this amplitude frequency response within our bandwidth. So this is more efficient approach, mean squared error equalizer. It considers both inter-symbol interference and the noise as well. Also, you need to remember that noise will actually also affect your impulse response evaluation. What you will receive will not be clean impulse response, it will be noisy impulse response, yes? So how does it work? Basically, you need to know original data. So basically that means that you are forced to send some special symbol sequences which are already known by receiver. This is the only way it can check if it receives data correctly or not. Yes. So basically these are some special sequences consisting of known symbols and the known order of these symbols, so that it's possible to actually evaluate number of errors. Yes, this is quite often used, for example, in mobile communication when you have seen, for example, some training data, yes, or in frames and so forth. This is actually exactly that, some special code sequence to calculate easier equalizer and to evaluate its efficiency, yes? So we need to know what we should receive and what we have received. And basically, then we find what our equalizer produces. Yes, and ideally, what we want to have is that these equalizer output values should be exactly the same as these ideal transmitted values. Yes. However, yes, our received, so we can say that, for example, these received are our ideal multiplied by each channel. Well, it's not really multiplied, it's like convolution after all, yes? In here we also can say that this is a convolution, but other than that, like this. So these are our, well, I think it's even better to just draw schematics. So our transmitter produces data A. Okay. Yes. Then we have channel which produces data RK. Then we have equalizer which produces QK. And what we want is to have this QK the same as this AK. And the only way to check if it is true is to actually know this AK. So what is going to happen once we have done this equalizing, we are going to compare this Q, what we have actually received, with this A, what we were expecting to receive. Yes, and accordingly, based on the results of this comparison, we are going to tweak our equalizer a little bit to make it operate better. Yes, so that's some iterative approach. Yes, so let's see how it works. So the expression for calculation of the received symbol is simple discrete convolution represented by this formula, where we have this as a received symbol, and this is our equalizer impulse response, what we have so far. Yes, so we have to have some equalizer. It may be better equalizer, but at least this is some starting point which we are going to optimize furthermore. Yes, so we need to set some equalizer. For example, this can easily be set at the beginning to 0, 0, 0, 0, 0, or for example 1, 0, 0, 0, 0, like this. Yes, easily. Then we are going to update it so that it has better match to original data. Now we want to have minimum error. So our original data minus our equalized data squared and averaged should be as close to 0 as possible. So this is mean square error formula, right? And we want it to be 0. Now you can remember some high mathematics courses, yes, that in order to minimize some function, we have to actually find its derivative and set this derivative equal to 0. Yes, so this is going to be a gradient because this function, yes, in more particular case, this qk, which is again this convolution of received symbol and equalizer symbol, which are unknown. Basically, these we do not know. And there are in total n of these values. So we are going to find derivative for each of these values. For example, for h0, for h1, for h3, or 2, and so forth, up to hn. So in total, we are going to find n derivatives and set each of them equal to 0. Yes, and in general form, it will look like this, where we have this. Well, we'll talk right now. What is this alpha and what is this phi? So basically, once we have these in our hands, we can express our equalizer values in matrix form as this solution. So what we need is to find this phi matrix and alpha vector. Now, what are those phi matrix and alpha vectors? Phi matrix is autocorrelation matrix of received data. Yes, so basically we find autocorrelation matrix. So in practical part of today's course, I will speak of this more and show you examples. Yes, but for now, let us just say that it's autocorrelation matrix. If you do not know how it should look like, you will see it clearly in practical exercise today. I will show you how this matrix is formed and what it is actually. Yes. Now, the alpha is the vector of cross correlation between some transmitted symbol, one symbol, AK, and each possible received symbol, RK. So, for example, in CAM16 modulation, once you transmit, I don't know, for example, symbol 5, you need to find cross correlation with all symbols starting from S1 and ending to S16. So that is going to be a vector of 16 values for cross correlation. Of course, this cross correlation will be maximum exactly for another symbol S5. Yes, with symbol S5, this cross correlation should be maximum. And for the other symbols, it will be smaller. And furthermore, it will be within the length of the impulse response window. Wait, no, not 16, but n. I'm sorry, not 16, but even n plus 1. How many symbols we have to consider in equalizer? Yes. So what we need to do is to find this gradient, yes, which is derivative of this equation, and basically we'll have this to be solved. But instead of that, we are going to actually find this autocorrelation matrix and find these cross-correlation vectors, and then simply calculate this matrix multiplication. Here we have inverse. Now you need to consider that not every matrix has inverse, yes, but there is also a so-called pseudo-inverse, pinf, in MATLAB function, which always produces some inverse result. Yes, so it's possible to solve this equation. And the second case is so-called iterative solution, step by step, when we have to spend some steps to find it basically not in a single go. Here we can calculate this matrix multiplication once and we have result. Yes. Now, however, if we were to start with some initial values, for example, 1, 0, 0, 0, 0, yes, and slowly, step by step, approach the correct value, then it will ask for us, for example, I don't know, for example, 50 steps, yes, to find the same solution as we would have find for matrix. And today in practical exercise, we are going to use these two methods and compare them. They should produce the same equalizers. However, in this case, we are going to use optimization procedure called gradient descent method, yes, which again is quite often used in machine learning. Now, for local students, I usually read the second course in parallel with this course, and I tell them some basic concepts about machine learning. Here, I would recommend you going to Coursera and finding course called Machine Learning, yes, from Stanford University. And one of the first lectures will explain this gradient descent method in more details. It's in English, so it should be no problem to understand for you. And the idea is that we update these equalizer coefficients step by step until we consider that it's good enough. Yes. A little bit more details is also provided, I believe, in this material and also here. Yes. So vector of received signal samples. That's what we are going to do. Here we have this AK. Now, coefficients of the equalizer here are C, yes. Well, at any rate, during the practical exercise, we are going to actually dig into this and get better understanding of what is cross-correlation matrix, what is autocorrelation matrix, and so forth. Oh, sorry. Now, before we finish this lecture part, I'd like to make few words about adaptive equalizers. What is different in there? We already have observed that the problem in real-world mobile telecommunications is that this impulse response is going to be time variable. Yes, it's not going to be fixed. So for that reason, your equalizer will also have to adjust all the time. Yes, so you will have to measure impulse response and update equalizer, or you will have to use any other possible way to control how your equalizer works. Because evaluating impulse response is not so easy task, especially during the movement, and sometimes there are alternatives. And well, today I'm accordingly going to mention a few of them. So what we need to do is to actually evaluate the number of errors. So for adaptive equalizers, we have to use some pilot signals. Yes, pilot signals sending a priori known data. So basically, we have to expect some specific data and then compare what we have received and what we should have received. And this way, we calculate the number of errors. Based on this number of errors, we make decision, should we update our equalizer or not? Yes, and there are multiple methods that can be used to accordingly perform this update, such as least mean squares method, recursive minimum squares method, constant modulus algorithm method, and so forth. But in all these cases, we are going to need this training sequence, this data which is previously known by us. Yes, And of course, some filter, finite impulse response filter, which is our equalizers with coefficients we are going to update. Yes. So here you can see diagram, so-called generalized diagram, which shows you 3 possible cases of such adaptive equalizers, depending on where is this switch position. So we can use for error control. So basically the idea is the same. So we have as a hard our equalizer, which can be evaluated, for example, by using MSE method, yes. Then we have some adjusting schematic, yes. So we need to somehow adjust this equalizer based on some decision and errors. Yes, so we need to know how much errors we have and based on our decision. Yes, so depending on what information is used for this error calculation, yes, so at any rate we have to find how much we have these errors. We need to know this number of errors, and there are 3 ways we can find this out. First of all, this is going to be demodulating decision, yes, and basically this way we can observe that, for example, because of using some codes that can correct errors, and we observe situation that we have too many errors that cannot be corrected by our codes, then even without this training sequence, we can know that our equalizer is not really doing good. Yes, so we need to adjust our equalizer until our error correction codes will tell us that everything is fine. Another possible way is to send previously known data training sequence. Yes, in that case, we don't have this decision basically needed. We can just compare what we have received after equalizer with what we should have received and find how many mismatches we have. Another possible way is to actually use some symbol statistics. This is actually completely blind mode, right? When we have no information about impulse response and so forth. This is the most complicated, as you imagine, the most difficult case. Yes, how to make it completely independent of nothing. Yes, but of course it will never be so good as any other type. Yes, it will be decent, maybe it will work, but compared to training sequences, for example, it will still not perform so well. Yes, so yes, here we can say that training sequence is some specific special previously known periodical sequence that has to be sent often enough, yes, with sufficient frequency, yes, considering that we can have slow and fast fading. Now, feedback is used to update filters coefficients based on how many errors we have, yes, and blind operation mode, no prior information about channel is available at all. So we use so-called Kalman filtering in this particular case, which is also a topic of an entire new course. Yes, so you might watch up Kalman filtering. It's not even used only for equalizing. This is quite universal method that can be used for many other applications as well. Basically for control systems, for making complex information processing systems when you have, for example, GPS data and inertial data to operate, provide you navigation information, for example, in cases when it is expected to have some GPS signal shortage. So you enter some tunnel, yes, with your car, no GPS signal is present in tunnel. However, because of the inertial sensors and sophisticated Kalman filtering processing, you still know where you are located, even without GPS signal. Yes, once GPS signal returns, your position precision will improve again, will be much more precise, but still it's something like that. So Kalman filtering is not only used for equalizers, right? Okay, that would be for the lecture part today all. Yes, and on our next part today, in 10 minutes, we are going to try and make some MSE equalizers and see how do they work. Yes, so see you in 10 minutes. And thank you for now. So in 10 minutes, we will continue.